All right, hello everyone and welcome to Virtual Office Hours. Today we'll focus on linear PDEs, like generalities, and not wave equation yet, next time. But hello. So just if you have any questions, just ask away and then be happy to answer. Hi. Yeah, sure, no problem. Okay, so problem 13. Let me get the different book. So let's see, problem 13. Oh, I'm guessing you mean from 1.2, right? Okay, so the question is, use the coordinate method to solve the following PDE. Ux plus 2uy plus 2x minus yu. And as I said, to simplify, just put the right-hand side equals 0. Now, why use the coordinate method? Well, for this example, so for this example, again, it's a first order PDE, so there are not that many methods. There's one, the geometric method, which talked about with the method of characteristics, which doesn't really apply here because we don't have a directional derivative. We just have this here, but then we have this u factor. You could make it disappear like the other problem on the homework 1, but I think really the best way of doing this is using the coordinate method. And well, here you have one factor, so maybe you can use x prime be 2x minus y. And well, for the other one, maybe the right-hand side helps because you have 2x squared plus 3xy minus 2y squared. And I believe you can factor this out as 2x minus y. And then let's see, probably, so you want minus 2y, so maybe plus 2y. And maybe, let's see, to make this work, we have 4xy and probably x plus 2y. I know in America they're amazing at factoring this out, so you probably know the answer better than me. So 2x squared plus 4xy minus xy, yeah, so that would work. So which might say maybe you can use x plus 2y as the right-hand side. And then, well, all you do, you use the chain rule. So du over dx, that becomes du over dx prime over dx, plus du over dy prime over dx, which becomes ux prime, and then times 2, plus uy prime times 1. So if you differentiate that with respect to x, you get 2. That with respect to x, you get 1. So we get 2ux prime plus uy prime. And then for the other one, you can use the chain rule again. So uy, so du over dy, that is du over dx prime over dy, plus du over dy prime over dy, and that becomes ux prime, and then dx prime over dy, that's minus 1, plus uy prime, dy prime over dy, that is 2. So you get minus ux prime plus 2uy prime. And by the way, so if it really bothers you to figure out what the variables are, you could always say do ax plus by and then cx plus dy, use the Chen-Lu, and then choose your constant so that you have a nice simplification. So it's definitely another way of doing this. Now, you want to plug this into the PDE, so ux then becomes 2ux prime plus uy prime, and then plus 2 times uy, which becomes minus ux prime plus 2 uy prime. This thing, we already had it here, so plus x prime u equals 0, and then 2ux prime plus uy prime minus 2ux prime plus 4uy prime plus x prime u equals 0. And then, wonder maybe I used the indices. I don't know, I think it's okay. Then, notice there's a simplification. This and this simplifies, and you have 5uy prime plus x prime u equals 0. And this is actually an ODE if you want, because it's just an equation with the y prime derivatives. So it becomes, if you want, 5uy prime equals minus x prime u, and so if you want uy prime equals minus x prime over 5u. And this is really the same, if you want, as the ODE in Math 3D, y prime equals ky. So what this means, except this is your new k here, so what this tells you is that u equals, so constant with respect to y prime, so I think any function of x prime times e of minus x prime over 5, our function, y prime. So again, notice with respect to y prime, this is a constant, and this is also a constant. So that works, and then that gives us a solution. So uxy, it's any function of, oh no, I forgot the variables. Let's see, 2x minus y, I think. E of minus 2x minus y, and then, okay, I think I had 2x plus y. I think. No, I think maybe x plus 2y or something. Man. Let me check. So 2x squared plus 4, yeah, that's what it is. And then over 5. Which, if you want, you don't have to simplify, but you can write as f of 2x minus y, e of minus this whole shebang. So minus 4x squared, again, 4xy minus xy, so 3xy minus 3xy, and then minus 4y squared, so plus 4y squared over 5. So a completely explicit formulation of this problem. All right, that's good. So there's but that was the first question. Then well, okay, why the coordinate method is a valid solution? Because it simplifies your PDE. It tells you that if you change your coordinates, then the PDE becomes a simple ODE. This is why it works. For finding the coordinates, it's pure luck, right? But you can always guess ax plus by, cx plus dy, at least for simple ones. For more complicated ones, we'll see it's more complicated. So like for the heat equation, we'll see it's more complicated change of variables. And again, you have to understand, this is not, and I already said this is not like a regular class. It's not like Math 3D where we give you a recipe and you apply it. In PDEs, there's lots of creativity involved. That's why it's way harder than other math subjects, You always have to figure out what the correct change of variables is. But again, for our class, it's fine. And yeah, and then, okay, maybe let me answer other questions as well. Let's see, for a, as a refresher to uniqueness, okay, 1.5, problem 1. Oh, 1.5, sorry. Well, I mean, you check U at L because the boundary condition is UL equals 0. So it's not arbitrary. It's like the condition that's given to you. Just like in ODEs, you have y double prime of 0 equals something. You know, we specify y of 0, let's say is 2, y of 3, y prime of 0 is 5. Well, that's a condition that's given to you. Okay, all right, so 4a, 4b, some people ask about this. Ooh, I love that problem. Okay, oh, maybe I shouldn't say a lot about this. And then I'll answer the other question. So 4a, 4b. So consider, again, very complicated PDE, Laplacian of u equals f, and with the Neumann boundary condition, sorry, this thing, equals 0. And I think it's in a three-dimensional region, so it's in, so f of x, y, z in D. And maybe I didn't mention this, but the Laplacian, well, in three variables is uxx plus uyy plus uzz. And one thing we'll need soon, well, remember the gradient in three dimensions is ux, uy, uz. If you, let's say you take the divergence of that. That gives you the first component with respect to x, the second component with respect to y, the third component with respect to z. That's the definition of the divergence of a vector field. But notice that's precisely uxx plus uyy plus uzz, and which is the Laplacian. So for, I guess for part B, we kind of need this fact. Laplacian of u is the divergence of this. Okay, first of all, I think the first question says, what can we surely add to this? Any solution to get another solution? Well, for instance, I think you can just add a constant, you see? Because if you have Laplacian of u plus a constant, well, if you take the second derivatives of the constant, well, it's still a solution. Okay. And also, what does this mean? Remember, this means the gradient of u plus the normal vector. So again, you have this 3D region and maybe a normal vector here. Well, if you add another constant to this, then because we're taking derivatives, the derivative of u plus a constant dotted with n is the same thing as the derivative of u dotted with n. So really the answer is we can add any constant. And it would still be a solution. So in particular, there's not a uniqueness because you can add any constant. Okay, and then for 4b, well, we have to use the divergence theorem and the PDE to show that if this has a solution, then the triple integral of f has to be 0. But look, what is the triple integral of f here? By the PDE. And again, if you're ever stuck, use the freaking PDE. You get the triple integral over d of the Laplacian of u. And you might say, what in the world does that have to do with divergence theorem? Well, remember the Laplacian is a hidden divergence. So this is the triple integral over d of divergence of du, f on dx, dy, dz. And now remember what the divergence theorem says. The divergence theorem says that the triple integral of the divergence, so suppose you have any vector field, the triple integral of f, the divergence of f, dx, dy, dz, is the same thing as the double integral over the boundary, so dt, of f dotted with n ds. Okay? Well, it's the same thing here, except f is just a gradient of u, so this becomes the double integral over the boundary of d of the gradient dotted with n ds. But remember, that's precisely the normal derivative. N ds. And remember, by assumption, we have that this is 0. So we do get that the necessary condition is the triple integral of f to be 0. In particular, suppose you choose a function that does not have this property, then it means there is no solution to this PDE. Well, we're kind of screwed. Let's see, number 6. Okay. Okay, so let's solve it, yeah. Well, I mean, let's see. If you give me the answer, let's see if it solves the PDE. So, and by the way, it can't be f because you also have this initial condition. So, and maybe the general solution is f of minus 1 over y minus x squared. But remember, you also have to plug in it's not initial, but let's say boundary condition in this case. But why not? Let's solve this. So, which one number you mean? I guess you mean number 6 and 1.5 by this one. Okay, but yeah, let me solve this. I think it's easier to be solved and explained. Yeah, 1.5 number 6. Okay, so let's do ux plus 2xy squared dy equals 0 with this Dirichlet condition, ux0 equals phi of x. Well, this becomes again what's called this typical first order PDE, which in theory we know how to solve. So one thing we know is that 1 comma 2xy squared dotted with ux uy equals 0. So in other words, by our discussion of first order linear PDE, what we want to find curves y equals to yx, which are parallel to this vector v. So what we want the slope dy over dx equals to the slope of v, which is 2xy squared divided by 1, and then you use a separation of variables thingy, so dy over y squared equals 2x dx, and integrate, so you get minus 1 over y, I believe, equals x squared plus a constant, so y becomes minus 1 over x squared plus a constant. And then essentially what you want to solve for that constant, so y times x squared plus c equals minus 1, and then yx squared plus cy equals minus 1, and then, let me see, maybe, well, I guess I can erase this now. We get cy equals minus 1 minus y, I guess x squared y, then let's do this, x squared y, and then constant equals minus 1 minus x squared y over y. And lastly, this becomes minus 1 over y minus x squared. So in other words, the solution, again, without the boundary condition, so the general solution, uxy, becomes any function of minus x squared minus 1 over y. Which, it's really the same thing as, which is the correct answer, the one you said. If you want, if f of this is true, then also f of minus this is true. So you can even make it cleaner by saying any function of x squared plus 1 over y. Okay, so we're not done though, because this is the general solution, and now we want to do the plug in the boundary condition. So let's figure out what f is. Well, let's see. Well, u of x0, that is f of. Oh wait, this is interesting. Is that correct? Actually, let's see, because we can't plug in u of x0. What the hell? Okay. F of x. The promise is infinity, so I don't even know. Maybe is that the typo? Let me just check that. That is strange. Now I see why you stopped on this. Okay. It doesn't even give solutions. But the only thing I can think of is, let me just think about this, because it's weird. You can't just plug it in. But let's look at. It's possible that it's just a typo. Yeah. I know that's the boundary condition for this, but the problem is, well, here you have your solution. How can you plug in u of x0 in this thing? Because if you plug in y equals 0, this becomes f of infinity or negative infinity. And then the question is, how can this point be equal to phi of x? So that's why I'm wondering if they meant maybe they meant u of 0y, because that would make more sense. But let me just look at the PDE again. So ux plus 2 x squared xy squared equals 0. Well, I guess if you plug in u of x0, you have a 0 here. So you have ux x0 equals 0. Then basically, so that becomes, but then ux x0, that becomes phi prime. So you see, so if ux 0 equals phi of x, then the derivative, so see, it's a function purely of x and a function purely of x. So if you differentiate this, you get phi prime of x. So technically what this means is that phi is a constant, which is not necessarily true. So the only thing I can think of really in this problem, unless it's possible that I made a mistake, but you have the same answer as me. So the only thing I can think of is simply that, let's see, well, phi has to be the constant function, and this forces f to be the constant function. So that is strange. No, but for 1.5, that's the boundary condition. For at least my 1.5.6 says u of x0 is phi of x. I don't know if that's correct. I don't know about you, but my boundary condition says this: ux0 is phi of x, and that's for 1.5 number 6. Not sure. Anyway, I'll think about this a bit, and then, yeah, let's do 1.6 number 6. Let's see. Okay, and of course we can go over it, it's fine. Okay, so let's say 1.6 number 6, that's maybe better. And then I'll also do the sketching part. I am running out of battery, so if at some point my phone stops, my apologies. But let's see. Oh, it's possible, yeah. I mean, I have the second edition. I don't know if that helps. So let's do 3uy plus uxy equals 0. Okay. And I should talk to the department because they gave this. Okay, so what's the type of this PDE? Well, again, this is just a junk term. It's like a lower order term. And this is really, there's no uxx term, plus 1 uxy, plus 0 uyy, plus 3uy equals 0. And then what we get, this is A, B, and C. Well, let's calculate the discriminant. That's 1 squared minus 4 times 0 times 0, which is 1, and it's a positive discriminant. So I'm guessing it's like the wave equation. So that becomes a hyperbolic. That's true. And then so that's a hyperbolic equation. And then find a general solution. Well, notice this is actually kind of almost like an ODE in X. So because if we let V be Uy, then this equation just becomes 3V plus, so Uxy, that's Uyx, and that's Vx. So 3V plus Vx equals 0. And then this is just an ODE in V. So Vx equals minus 3V. So V of x, so V just becomes a constant with respect to y. So f of y, e of minus 3x, I think. And indeed that is true. And then what do we have? But V is uy, so uy equals f of y, e of minus 3x. Well, what that tells us is u of xy. You integrate that with respect to y. This is just a constant. This becomes an antiderivative of f. So fy e of minus 3x. And then the constant is, well, it's constant with respect to y, so it's any function of x. And indeed, you can check that. Uy, this disappears, this becomes little f, and the other term is e of minus 3x. So that is the general solution. And then all we have to do is solve it with the auxiliary conditions. So let's solve it with u of x 0. So I think u of x 0 equals e of minus 3x, and uy x 0 equals 0, I believe. Okay, let's see. If you plug in u of x 0, that becomes f of y times 1 plus g of 0. Oh, sorry, g of x. No, I don't know what I'm thinking of today. So you plug in y equals 0. So f of 0, e of minus 3x plus g of x. And we know this is e of minus 3x. So I'm guessing this means maybe f of 0 is 1 and g of x is 0. But well, let's see. Then this means, so we have this equality. So all that we can conclude is f of 0 plus g of x, e of 3x equals 1. That's one thing. And now let's calculate the derivative. So uy, so you differentiate this with respect to y, so you get f prime of y, e of minus 3x. And now what you get? Uy, and then this disappears with respect to y. So uy x0, that becomes f prime of y, f prime of 0, e of minus 3x, and that gives you 0. Okay. And that gives you, therefore, f prime of 0 equals 0. So essentially it seems, so I think there does exist a solution, but I'm guessing it's not unique. Because you see, whenever you have a function that satisfies this equation, namely f of 0 plus g of x, e of 3x equals 1, with the condition that f prime of 0 equals 0, then any function of this form solves it. So, but let me just think. So, g of x. So, yeah. So let's try to come up with examples of that and see if it works. Let me think. So, for example, g of x. If you do g of x equals e of minus 3x. And then let's say f of x or f of y, if you want, is y squared. I don't know. Then we do have f of 0 plus g of x e of 3x. That is indeed 1. And the derivative of f with respect to y at 0, it's 0. And that would, let's say, give you the solution. U of xy equals y squared e of minus 3x plus e of minus 3x. That would give you one solution. Another solution would be, I guess, let's say we keep this, but this time I think f of 0 equals 0. So f of y is the 0 function, and that would give you the solution. U of xy is, so 0 e of minus 3x plus e of minus 3x. And that would give you another solution of the PDE. So just think, whenever you're stuck, maybe there might be infinitely many solutions. So in other words, there's not more info that we can do. Okay, and then I think we had a request for 1.6. Let's see, well, 1.5, I'll do 1.5 number 5 later, but let's do someone asked me about 1.6 number 2. Okay, so 1.6 number 2. So just find the regions where this equation is elliptic, hyperbolic, or parabolic. So 1 plus x uxx plus 2xy uxy minus y squared uyy equals 0. And then we get, we can take the discriminant. D is 2xy squared minus 4 times 1 plus x times minus y squared. So that becomes 4x squared y squared. Again, plus 4 times 1 plus x times y squared. And that becomes 4x squared y squared plus 4y squared plus 4xy squared. And notice there's this 4. There's actually lots of common factors. So it's 4y squared, and then x squared plus x plus 1. And then we just want to figure out, when is this positive, when is this 0, when is this negative? Well, the nice thing is we have this term, which is positive everywhere except for the y equals 0. So already here we can say that on the x-axis, whenever y is 0, it's parabolic. Okay. So basically, from now on, since we're dealing with the other regions, we can just ignore this and just deal with the sign of x squared plus x plus 1. And so let's maybe factor this out. I think it becomes x plus 1/2 squared. Okay, x squared plus x plus, so minus 1/4 plus 1. And then, let me just see, I think that is correct. Seems too good to be true. But we get x plus 1/2 squared, and then plus 3/4. Correct. So x squared plus x plus 1. Yeah, and then basically, well, this is always positive. So I guess in any other region, this becomes a hyperbolic equation. Let me double check. That seems too good to be true. Squared minus 4 times 1 this, okay, so 4x squared y squared, that is correct, plus 4 times 1 plus x times y squared, and then that becomes this 4y squared plus, maybe it makes sense, yeah. Oh, unless I made a mistake, I think that makes sense, but oh no. Are you still awake, by the way? Everyone's silent. I hope you didn't just disappear. Like, that would not be nice. Okay, but anyway, now let's do 1.5 number 5. So x plus wait. No, actually. Yeah, never mind. Okay, sorry. I'm having a senior moment. Okay, so let's do ux. I'm sure you're like all like so amazed by PDEs. That's why. It's good. So ux plus y uy equals 0, and then we have the boundary condition ux 0 equals phi of x. Okay, and then, well, let's first find a general solution of this. So this is again this wonderful geometric method. So this thing equals 0. So we're looking for curves y such that dy over dx equals the slope of that, so y over 1, and then solve this. Well, I mean, technically it's just exponential solution, so y of x, so y equals c e to the x, so solve for that constant, c is y e to the minus x, and then basically any function of y e to the minus x solves this. So solves this. And then the question is, well, for phi of x equals x, so also, yeah, let's also do that. So u of x0 then becomes f of, so 0 e of minus x, so 0, and that's phi of x. And then, yeah, oh, okay, maybe that makes sense. So u of x is, so in other words, f of 0 is phi of x. In particular, look, this is constant, right? So if let's say phi of x equals x, okay? Then we get f of 0 equals x. But that is a problem. How can a constant be the same as being x? That doesn't really make sense. Okay? So in that case, because we have this contradiction, so let's say choose x equals 1 and x equals 2, then you get 1 equals 2. We have a contradiction, and that's why no solutions would exist. On the other hand, suppose phi of x is 1. Now suppose phi of x is 1. That means f of 0 equals 1. What does that mean? It means any function with f of 0 equals 1 works for this PDE. So in other words, there are many solutions. For instance, you see, take, let's say, I don't know, f of z be z squared plus 1. That satisfies f of 0 equals 1. Then one solution would be y(e) of minus x squared plus 1. And then you can indeed check that u of x0 is the function 1. On the other hand, why not take f of z be cosine of x? Sorry, cosine of z. That also satisfies f of 0 equals 1. And the solution would be cosine y(e) of minus x plus 1. You see, because if you plug, sorry, not plus 1. Cosine e of y(e) minus x. It would still satisfy if y is 0, then f u of x0 would still be 1, which is our function, which satisfies the boundary condition 1. So it makes sense, I think. Yeah. I think, is that all? Let's see, 1.6, number 6. Yeah, I did 1.6, number 6. Did I do all the homework for you? No, it's okay. 1.5, number 5. 1.6, number 2. Yeah, I think I answered all the questions. Woo! Yeah, I mean, we kind of went over time, but does anyone have any other questions? Also, sorry about the wave equation today. I was so excited to give you an elegant solution, and then I just ruined it at the end. But maybe I'll do a YouTube video to make up for it. We'll see. I still owe you like 10,000 videos, but hopefully soon my schedule is a bit lighter, because I also have to apply for math jobs, so that's why it's taking all my time. You're welcome, you're welcome. You're welcome. One more minute, and if no one has any questions, I can stop it and go home and have dinner. Alright, I think we can just call it a day. So thank you for everything, and then yeah, see you Friday, or I have office hours tomorrow as well if you want to join. Alright, bye.